In this last video in section 2.6, we're going to look at finding the center of mass of a lamina bounded by two functions. I have not gone through any of the theoretical development. I'm skipping right to the actual formulas. Now, the formulas are similar to what we did in the previous video. So let's start with the mass formula, the total mass formula. You will remember that the total mass formula was rho, or the density, times the integral of f of x dx. So we had mass was equal to rho times the integral from a to b of f of x dx. The only difference now is it's f of x minus g of x, the difference between the two functions, where it's important to understand that f of x is the function on top, and g of x would be the function on the bottom. G of x is on the bottom, f of x would be the function on the top. So it's the top function minus the bottom function. Now, finding the moments about the x-axis and the y-axis are also very similar. Remember, the moment about the x-axis was the density times the integral of 1/2 f of x squared. Well, now it's 1/2 f of x squared minus g of x squared. Now, be careful. Common mistake here is rather than squaring f of x, squaring g of x and subtracting them, which is what you're supposed to do, sometimes people will accidentally take f of x and subtract g of x like you did here and then square it. No. You square the function first, then subtract them times 1/2. And then, of course, the moment about the y-axis was m sub y is rho times the integral from a to b of x times f of x. Now it's x times f of x minus g of x. So it's x times the difference between the function above minus the function below. And then, of course, the coordinates of the center of mass, same formulas. So we just have to find the difference between our functions. That's pretty much the significant difference here. So let's take a look at our first example. Now, in these examples, I've skipped a lot of the math, just getting right to the new stuff. So here we have two functions. F of x is 1 minus x squared, and g of x is x minus 1. We're looking for the region R bounded above and below by those two graphs. Find the centroid. Centroid is the center of mass of the region. So you have to find the points of intersection. So again, you could use that by Desmos, or you could do it algebraically. Either way, but you need to find the centers, or the points of intersection. So you have those. And now let's find the total mass. So the total mass is density times the integral from 1 to negative 2. That comes from our points of intersection, the x values. We're doing it along the x-axis. And so we have f of x, the top function. F of x is the top function. G of x is the bottom function. So the top function minus the bottom function. And so simplifying that, you end up with this, and then integrating it, you end up with this, and evaluating it, you end up with 9/2. So the total mass is 9/2. Now here's where I didn't show pretty much any of the work. I basically set up the integral and gave you the answer. So the total moment about the x-axis is rho times the integral from negative 2 to 1 of 1/2, and here's where you have to be careful, of 1 minus x squared squared minus x minus 1 squared. So I know that you guys can square 1 minus x squared, you can square x minus 1, and you can do the algebra there. And then it just becomes a simple set of terms to integrate each term by term, using the power rule for antiderivatives, and you end up with negative 27/10. Then the y value of the moment is the density from negative 2 to 1 of x times the difference. Same thing that we did up here. So this is going to be this times x. Don't forget to multiply it by x. And so, again, you're just going to have a polynomial. Find the antiderivative of each term of the polynomial, term by term, and you end up with negative 9/4. And then we just put those all together. The x value of the centroid, or the center of mass, is the total moment about the y-axis divided by the mass, which is negative 1/2. And the y value of the centroid is the total mass, total moment about the x-axis divided by the total mass, which is negative 3/5. So there's just a little bit more algebra. As far as the integrating goes, it usually isn't any more difficult than we've done before. One more example. Find the centroid of the region bounded by the curves y equals x to the 5th and x equals y to the 5th. Now, being tricky right here, x equals y to the 5th, you have to change that into y equals x to the 1/5 power, or the 5th root of x. But I prefer to write it as x to the 1/5 because we can integrate it that way. All right, so then graph these in Desmos. And we're only interested in, I didn't write it in here, but I kind of sketched it in there, in the first quadrant. So we're only interested in the part of the graph in the first quadrant. So we've got this area in here. And so the graph that's on top is, this is the graph on top. And then x to the 5th is the graph on the bottom. And so, again, the total mass, we have the function on top minus the function on the bottom. And so x to the 1/5, finding the antiderivative is 5/6 x to the 6/5. X to the 5th becomes 1/6 x to the 6th. Evaluating from 1 to 0, we get the total mass is 2/3. Then, finding the total moment about the x-axis, brought the 1/2 out in front. Again, don't forget you have to square the top function. I'm not going to call it f of x or g of x. We always call f of x the top function, so we can call this f of x if we want and call that g of x, but it's the top function squared minus the bottom function squared. So x to the 1/5 squared is 2/5. X to the 10th squared, x to the 5th squared is x to the 10th. Finding the antiderivative of that, we get this. Evaluated from 1 to 0, we get 24/77. And then finally, the total moment about the y-axis is x times the top function minus the bottom function. And so x to the 1/5 times x is x to the 6/5. X to the 5th times x is x to the 6th. Finding the antiderivatives, evaluating from 1 to 0, we get the total moment about the y-axis is 24/77. Putting it all together, we get the x value of the centroid is 36/77. The y value of the centroid, I made some little arithmetic mistakes here, just ignore those, is 36/77 as well. And so that is the process for finding the center of mass, or centroid, of a lamina, which is created between two curves. So, just again, so what we're doing here is you've got a curve and you've got another curve. And here is our region. And so you've got g of x is the bottom one, and we've got f of x is the top one. And so what we're doing is we're taking this region in here, and we are finding its center of mass. Some point in the center of this thing, where it would balance. That is what we are doing. And so this whole thing here is called a lamina. The center of mass is called the centroid. All right, and that finishes up everything in section 2.6, and along with that, we are done with chapter 2. Right. See you in chapter 3.